Okay, so we've got one more session before lunch, and trust me, it'll be worth waiting for. So we're here, of course, in Boston, and we're in the shadow of MIT, which, as I think everyone knows, is kind of an epicenter for innovation, and Dr. Ellen Roche's lab is no exception. I won't take too much of her time because I know she has a massive amount of information to share with us. A beautiful example of blending the virtual and the real world. So please join me in welcoming Ellen to the stage.
Thank you very much. Thanks, everyone. It's a pleasure to be here, and thanks for the invitation. My title is now Associate Professor, so yay for promotions, but I'm happy to... All right. Okay, so I'm going to talk today a little bit about the virtual world, but also into the physical world, as was mentioned. So my research at MIT since 2017 has been focused on cyclically dynamic organs. So we're interested in muscular pumps that are in constant motion, like the diaphragm that moves air in and out of the lung. My mic, that moves blood around the body. So we're interested in modeling these with virtual and physical and preclinical models, but also designing devices to treat these cyclically moving organs when they become diseased. And I think of this kind of work as a dance or a kind of coordinated effort between industry, clinical partners, and academic labs. And I think we could all work together and bring unique tools to this kind of trifecta to move things along. Our work, as I mentioned, is benchtop models, computational, and animal models. And we work with industry so that we can have better test beds to test devices. And we work with the clinic to test out treatment options and to get a better understanding of disease. And I'm just going to step through a few case studies of work that we've done using these tools, and I'll highlight kind of out of the three pillars that I mentioned, you know, how it was initiated and how it came about. So the first case study I'll give is an example of a biomimetic soft robotic sleeve that we use to mimic aortic stenosis. We wanted to mimic the biomechanics and the hemodynamics of aortic stenosis and ventricular pressure overload. So this is kind of a nice follow-on from the last talk. This was a collaboration between MIT, Mass General Hospital, and then Cleveland Clinic. And Yiling, my graduate student, is here. He was involved in this effort and a lot of what I'll talk about today, along with other lab members. So you all likely know what aortic stenosis is. It's a disease where the aortic valve becomes narrowed, and there's high pressure gradients across it. We saw this need for an accurate way to mimic different types of aortic stenosis. As well, in addition to degenerative valve disease, can we mimic congenital valve disease? So we designed this sleeve. We use soft robotic techniques a lot in our lab, so these soft devices. We use them to augment cardiac function, but also here to mimic disease models. So this is a sleeve with 3 pockets that can be wrapped around the aorta, and we can selectively fill these pockets to mimic different levels of aortic disease. And then we can use virtual modeling, as shown here. This modeling is done with X-flow, so depending on the pockets you actuate, if you fill 1 or 2 or 3 pockets, you get very different flow through the aorta. And this is a model of a porcine aorta. And you can see, depending on how many pockets that you fill, you can get very different velocity profiles. Of course, we need to validate this work. So we did in vivo testing on this. This is a pig model. We can measure cardiac function with echo, implant this device around the aorta. We can do MRI, 40 velocity encoded MRI to look at flow. And then we can fill these pockets to different degrees. We kept these pigs alive for 8 days, and on the terminal time point, we did LV catheterization so we could measure pressure volume loops. So you can see we can get a very degrees of aortic disease in vivo. On the left here, on your left, you can see one active pocket. So the teal is a healthy pressure volume loop throughout one cardiac cycle. And as we inflate one pocket, you get this narrower loop, so less volume, and a taller loop, so higher pressure gradient. And then if you do 2 pockets, both effects are pronounced even further, up to 3 pockets where you can get, basically no volume and really, really high pressure gradients. So a nice tunable model to mimic aortic stenosis at different levels. And then with the MRI, you can measure velocity and flow, and then flow through the aorta with these different pockets actuated. And then we can compare these to our CFD models, and we get a really nice match. The purple shows the MRI, and the green shows the CFD for aortic constriction percentage, but also peak flow velocity at various degrees of actuation of these pockets. We can also do cyclical actuation of the sleeve. So the video shows as we're inflating and deflating it actively with each cardiac cycle, and we can measure velocity at different points along the aortic arch. And you can see on the bottom right how we can get a range of different disease profiles and really vary both the volume and the pressure to mimic disease. So this work is a model to customize aortic flow patterns to model both aortic stenosis and congenital valvular defects. It starts to think about how we can use soft robotic tools to mimic disease and hemodynamics. And the next part, I'll talk about how we do this on a patient-specific level. And hopefully, if we can create these models virtually and physically, we can identify which patients are suitable for clinical intervention, but also use them to test and develop new therapies. So then we moved to trying to replicate not only aortic stenosis and pressure overload, but the ventricular stiffening that happens, as was mentioned in the last talk. And this is a patient-specific, completely synthetic of aortic stenosis and diastolic dysfunction. So what we do here, we take clinical data from patients with aortic stenosis. We get CT data, and we have some echo data and some LV catheterization. We create 3D models from the CT scan. And we use these 3D models to 3D print the left ventricle and the aorta in a patient-specific manner using a soft material. Now we have a sleeve around the ventricle, so we can modulate the compliance of the ventricle and the aortic sleeve, similar to the last part where we can mimic pressure overload. So this allows us some tunability in the various resistances and compliances of the system, so we can mimic pressure overload, but also ventricular stiffening. And then we can use these models to test interventions like aortic valve TAVR procedures, transcatheter aortic valve replacements. A little bit more on the ventricular sleeve. So this is made in a similar way. These sleeves are thermally formed, so we have multiple inflatable pockets. There's an inextensible fabric on the outside. These are patient-specific. Again, we did 15 different patients with these. And if you look at what we can see on echo, the left ventricle can get this nice contractile motion. And this sleeve can act as the pump when we connect this to a mock circulatory loop, so we don't need to connect it to a pulsatile pump. We can really try to tune the effective orifice area and the opening profile. So on the top row there is CT scans from patients. Underneath, you can see the opening profiles that we can get with the sleeve. So we can recreate it quite closely. We can also do multi-material 3D printing, so we can actually deposit calcifications on the leaflet, similar to what we see on the CT scan. And then we can use this to demonstrate the correct pressure gradients across the valve. On the bottom right there, you can just see how we can closely match the pressure gradient of a patient, because we have pressure data from LV catheterization of these patients. The gray bars show the patient, and the blue bars show our model. The pink is the multi-material 3D printing model, so we can match that pretty nicely. This just shows how much of a gradation we can get in the ventricular compliance from healthy to moderate to severe remodeling. And that's really by contracting with the left ventricular sleeve, but varying the degree to which we empty the sleeve so that we replicate diastolic dysfunction or ventricular stiffening. Finally, we were able to test interventions. So this is a transcatheter aortic valve replacement shown in the video. And what we can show is the hemodynamics that occur on a patient-specific level with different types of valves. So before we place the valve, you can see high pressure gradients between the left ventricle and the aorta. And then afterwards, you can see how those pressure gradients are reduced back to normal when the valve is placed and the aortic valve is opened up. I'll just show a quick video on this work on how we make these sleeves. We have a drawer of patient-specific hearts and sleeves in the lab, and this will just show a little bit more about how they're made.
In action and the motion of the aortic valve in disease, the team has fabricated sleeves similar to blood pressure cuffs that wrap around a printed heart and aorta. They tailored each sleeve's pockets such that when wrapped around their respective forms and connected to a small air pumping system, the sleeves could be tuned separately to realistically contract and constrict the printed models. By using patient-specific data, the researchers are able to accurately recreate the same heart pumping pressures and flows that were previously measured in a specific patient.
Okay, so just to kind of conclude this part of the talk, with these models, we can have enhanced control over pressure overload, ventricular compliance. We can recreate birth defects like congenital valve disease. We can modulate heart function completely synthetically, both virtually and physically, and we can simulate treatment. We'll move to another few case studies of working with different groups to use in silico, in vitro and in vivo models to test out therapies. This next kind of set of data is a collaboration with Stanford hospitals, particularly with Joseph Wu's group at Stanford. So here we use the living heart model. We have a structural simulation, and here we have a particle-based fluid structure. So we can do a fully coupled fluid structure interaction model, coupling both the fluid and structural domain. In this example, here we can show the velocity magnitude, which is really nice to be able to visualize, the internal ventricle, the wall deformation, and the flow as well. In this scenario, we were looking at mitral valve prolapse. So we developed an in silico model of the mitral valve. We can look at a structural model of the valve leaflets on the top left there, and we can look at a fluid model, and based on the integrity of the chordae, we can create different degrees of mitral regurgitation. So as we remove P1, P2, and different chordae, we can get varying degrees of regurgitation. And the Wu group had reached out to us to ask us about measuring the force in the chordae, because they have an experimental model that's shown here on the right, where they could actually measure the force in the chordae, and they wanted to model it to see if we could get similar results. And we were able to show that we could get similar force curves throughout the cardiac cycle with the chords. The same group were also looking at aortic root replacement planning and whether or not a straight graft versus a Valsalva graft was more beneficial when you think about the flow profiles and the vortices that occur above the aortic valve. So this is two different variations of the shunt that they can use. You can place these corrugations in the horizontal or the vertical configuration. And then we can look at doing a fluid structure interaction model again, where we can model the flow around the aortic valve in systole and diastole, and really look closely at the vortices that form, so that we can make some predictions about which is better for flow and for preventing thrombosis. So here you see the difference between a straight graft and a Valsalva graft. And you'll notice in the Valsalva graft, you get much better vortice formation during diastole in particular. So this is just an example of where we can kind of partner with different groups that are interested in asking very specific questions that these tools allow us to model, and a credit to Yilling for a lot of this work. Another piece of work that I'll describe briefly, I think I have time. I know I'm talking fast, but just to give kind of a high-level overview of some of these interactions. This is work that we did with Boston Children's Hospital, who are long-term collaborators of ours at MIT. We set out to build an artificial myocardium, and this was to connect. Originally, we were doing a sleeve to augment heart function in heart failure patients, and recently we moved to a benchtop model where we could connect organic tissue to a sleeve to recreate heart function on the bench. And we were looking at optimizing how we make this artificial myocardium with robotic methods. So which actuators do we use? How many layers do we use? What orientation do we put the actuators in? So we had a structural finite element model that allowed us to basically screen through a lot of different architectures and different designs. And in the end, we wanted to have realistic physiological left ventricular volume displacement or ejection fraction, realistic ventricular pressure generation, and also recreate the twisting motion that the heart sees. So this screening allowed us to optimize the design, and this is the model of the optimized design. So we have two layers. These are McKibben pneumatic that are placed both circumferentially and on the inner layer helically. So we can replicate really physiological, 70 to 80% volume displacement, correct pressures, and good ventricular twisting as well, about 8.5 degrees. Now we can couple this to using X-flow to fluid model, and we can look at basically what happens during the cardiac cycle and what happens resident fluid inside there, and really predict where we have low velocity regions, which we don't want to have because they may cause thrombosis if we were to use this in reality. So coupling that structural model to the fluid domain really helped us to figure out not just what has the best physiological parameters mechanically, but what would be the best kind of displacement to not trap blood or not have blood thrombus. So here you can just see when we realized this model. This is a physical model where we're in slow motion ejecting water from an artificial myocardium, but we can get about 70% ejection fraction and up to 130 millimeters of mercury pressure generated. And this was kind of helped by the virtual models that I showed you. Final example here is a group led by Dr. Ingeborg Fries at Boston Children's Hospital came to us, and they were interested in endocardial fibroelastosis. It's a rare heart disorder that affects children, and you get this thickening within the muscular lining of the heart chambers due to an increase in inelastic collagen and elastic fibers. They had some 4D MRI data that they wanted to do some modeling on to understand better what are the wall shear stresses and could they be linked to this condition, because they have a lot of in vitro work where they study the response to wall shear stress in Petri dishes, but they basically wanted to look at scale what are the wall shear stresses. So this is what the 4D MRI looked like, and we were able to kind of use this to generate a model. When we reconstructed the flow profile, you can see this. We got kind of imbalanced velocity vectors, so we took another approach to creating more accurate flow dynamics here. So we used a wall tracking algorithm. This is in 3D Slicer. We could take the kind of wall motion and recreate what happens to the ventricle walls during one cardiac cycle. And this is patient-specific, taken from a patient that has this EFE or endocardial fibroelastosis condition. Then we can use this to create a model of the internal left ventricle and use this kind of to impose the boundary conditions on a finite element model. So we can use that then to create a finite element simulation where the extracted wall displacement is accurate over one cycle. Now we can go and we can couple that and create an accurate fluid structure interaction model, and you can see how the flow profiles match what was measured in vivo but wasn't high resolution enough to really use. So here as I mentioned, we used XFlow, which was really beneficial for this, and then from that we could calculate wall shear stress and feed that back to them so they could correlate it with their ongoing research. Okay, I'll finish there. This is thanks to a huge interdisciplinary team of people that we have in the lab. Our collaborators are listed at the bottom there: Professor Nguyen at Cleveland, Professor Wu at Stanford, and Dr. Fries at Boston Children's Hospital. Yilling is here. He's worked with the Living Heart Project for many years now and has done additional beautiful work that I didn't have time to show here. And he's finalizing, but hopefully we can present again at another meeting. Chaglar does a lot of the fluid modeling work. Luca did a lot of the physical work. So huge thanks to that team and to my funders. And thanks to this group that I have the pleasure of working with. Thank you.
Wow. Okay. Well, congratulations. Thank you on all that work and for sharing it with us miraculously right on schedule.
I know. I told you I talk fast.
It's a testament to the precision of your work. Okay, so, but with that, I'm going, because I know you're already been incredibly patient. It's been an amazing morning. I know you want to talk about it. You want to get refreshed, refuel. It's time to break for lunch. Do we have any housekeeping? We do. So you do get lunch. Unfortunately, you're going to have to work for it because you're going to have to go back to where we were yesterday. The good news is you've got food, you've got the playground, you'll be able to tinker around. Oh, sorry. Yeah. You can use the demos, visit some of the researchers who were here today showing you the tools. The important thing is we're going to start promptly at 12:50, so you have 50 minutes. It will take some time to come back, fighting for elevators, so please leave 5 minutes in advance. And we're going to pick up after lunch, and we're going to start the really exciting session on the future of artificial intelligence and machine learning we had a taste of this morning. So join me again, once again, for thanking Ellen and the entire group for a fantastic morning.